At minus 50 degrees Celsius, a lead-acid battery retains barely half its cranking power. Diesel thickens into waxy gel. Hydraulic systems nearly freeze in place. Most machines quit. But across Siberia's winter corridors, KamAZ Arctic trucks keep pushing forward, hauling critical freight where breakdown isn't inconvenient, it's life-threatening. These vehicles were built for minus 60 degrees Celsius, and the engineering behind them contradicts nearly everything modern automotive design prioritizes. Subscribe to follow this ongoing investigation into extreme environment engineering, because what keeps these machines alive starts with a design principle most of the world abandoned decades ago. On the northern ice roads, cold is the only certainty. Supply convoys rely on vehicles that can survive where batteries drain in minutes and diesel thickens to wax. The KamAZ Arctic truck, especially the 6345 and 6350 series, anchors these routes, not for comfort or speed, but for the simple fact that nothing else lasts. Every detail is a response to the Siberian winter's physics. The cabin is built as a double skin shell, with dense polyurethane foam sandwiched between steel panels. This creates a thermal barrier that keeps the interior at plus 15 degrees Celsius, while the outside plunges to minus 55 degrees Celsius. Insulation alone is not enough. A 12-kilowatt diesel heater, backed by an auxiliary electric unit, pushes warm air through the cabin, battery compartment, and fuel tank. On the 2025 Yakutsk to Pevek run, drivers reported cabin temperatures steady enough to work barehanded, even as frost coated the glass. But warmth does not move freight. The KamAZ Arctic's core is its torque-heavy diesel engine, the 11.75-liter V8. The KamAZ 740 PKV1 delivers 1,434 Newton-meters of peak torque. What matters most is the torque plateau, flat from 800 to 1,600 revolutions per minute. In deep snow, where rolling resistance can double, this low rev torque lets the truck crawl forward without constant shifting or wheel spin. The design borrows from rally raids like Dakar, where low-speed torque is vital for climbing dunes, and in the Arctic for grinding through drifts and ice ridges. The chassis is a ladder frame made from high-strength, low-alloy steel, bolted and gusseted to spread massive loads. The KamAZ 6350, with its 8x8 drivetrain, hauls up to 10 tons across ice roads and frozen rivers. Reinforced axle housings and heat-treated hubs absorb shock from hidden fractures and sudden impacts, failures that could strand a convoy for days. When ice thins below safety margins, crews can offload cargo onto sleds, but the truck's structure is built to keep moving as long as the surface holds. Preheating is mandatory. Before every start, operators follow a strict sequence: cabin heater, fuel line heater, battery warming. The process takes up to 45 minutes, raising diesel to plus 5 degrees Celsius and batteries to plus 20 degrees Celsius. Skipping a step doubles the risk of a failed start or frozen fuel line, consequences that can halt an entire supply chain. These trucks are more than machines. On the Norilsk to Talnakh corridor, a stalled KamAZ can stop a mine or leave a settlement waiting for essentials. Insulation, torque-biased diesel, and ladder frame chassis are not luxuries, they are survival. Here, Arctic engineering begins with a platform that keeps moving when everything else stops. A UAZ Hunter parked on a frozen roadside is more than a vehicle. It is a toolkit for survival. In the Siberian winter, repair culture is not a hobby. It is the difference between moving and freezing. The Hunter's design speaks this language, carrying the legacy of the Soviet UAZ 469. Its ladder frame chassis, a rectangle of high-strength steel, runs on leaf springs and solid axles built to bend but not break. The crossmember beneath the engine, redesigned in 1975 after cold chamber tests exposed micro cracks, features rib stiffening and a wider profile. Soviet engineers increased its thickness to 12 millimeters using alloy 30 kHGSA so the frame could absorb thermal shocks without splitting. The entire crossmember bolts in, not welds, letting a stranded crew swap it out with only a socket set and a jack. No power tools and no heated garage required. The Hunter's starter motor, a notorious weak point in deep cold, can be removed in under 15 minutes. First, disconnect the battery. 4 bolts come out, the wiring harness is removed, and the unit pivots free from the bell housing. Mechanics in Yakutia keep spare brushes in their coat pockets, ready to rebuild a starter on the Tundra. Carburetor tuning is done with a screwdriver and a practiced ear, not a laptop. The idle mixture screw sits exposed, easy to adjust even with gloves on. If the choke diaphragm fails to seal at sub-zero, a replacement can be cut from a sheet of silicone and fitted on the spot. Rubber seals, once EPDM and prone to cracking at minus 30 degrees Celsius, have been swapped for fluorocarbon O-rings rated to minus 60 degrees Celsius, following lessons from decades of field failures. In the cold, every shortcut is a risk. Standard protocol is a battery warming blanket for 30 minutes, a splash of ether-based starter fluid if the crank is slow, and fuel lines preheated with a portable electric coil. The Hunter's transfer case is all manual. No electronics to freeze, just a lever connecting steel rods to sliding dog clutches. High, low, and neutral are selected by feel. If the linkage ices up, a mechanic can unbolt the cover and free it with a pry bar. Leaf springs, while primitive, can be re-arched with a sledgehammer and a block of wood, then bolted back in place. On the 2024 Arctic Science Convoy, a Hunter lost a shackle pin to metal fatigue at minus 52 degrees Celsius. The crew fashioned a replacement from a cut-down tent stake and drove another 300 kilometers before a proper repair. These rituals are not nostalgia, they are necessity. The 1975 crossmember upgrade, the choice of a ladder frame, the exposed transfer case, and the bolt-on starter all serve a single goal: field repairability. When the nearest town is a day's drive and rescue is uncertain, a vehicle must be fixable with what is on hand. The UAZ Hunter's mechanical simplicity is not a relic of the past. It is a deliberate answer to physics that do not negotiate. This philosophy, build it so anyone can fix it anywhere, lays the groundwork for the next challenge, adapting to terrain as unpredictable as the weather. The Hunter's field repair culture sets the stage for the ultra-low pressure tire systems and ground pressure tricks that follow, where adaptability is measured in centimeters of snow and the ability to keep moving when the road disappears. A Trekol operator's log from the Kolyma Basin, February 2023, reads, pressure at 38 kilopascals, snow depth 28 centimeters, forward speed 11 kilometers per hour, no sinkage. In the Russian Arctic, survival depends less on horsepower than on how a tire meets the ground. On soft muskeg or fresh snow, a standard truck tire, inflated to 250 kilopascals, presses down with over 15 kilopascals per square meter. The result is predictable. The truck sinks, wheels spin, and progress stops cold. Ultra-low pressure tires, as seen on Trekol and Avtoros Shaman vehicles, flip the script. By dropping inflation to as little as 30 kilopascals, less than a third of a typical off-road tire, the contact patch expands to as much as 2.5 square meters per tire. This spreads the vehicle's weight so ground pressure falls below 5 kilopascals per axle. On paper, a 10-ton truck presses the earth with less force per square centimeter than a person's foot. In practice, the vehicle glides over terrain that would trap almost anything else. The math is simple but relentless. Ground pressure equals load divided by contact area. A Trekol 4x4 weighing 3,600 kilograms spreads its mass across 4 tires at 35 kilopascals, resulting in just over 6 kilopascals ground pressure. That is less than a third of the bearing strength of compacted permafrost, enough to avoid breaking through the fragile crust in late spring. On deep snow, deflating to 30 kilopascals doubles the footprint, halving ground pressure and keeping sinkage under 5 centimeters. By contrast, a KamAZ Arctic truck on standard 425 by 85 R tires at 150 kilopascals has a contact patch of only 0.13 square meters per tire, pushing ground pressure to 12 kilopascals. That is manageable on solid ice, but risky on muskeg. Tire pressure is not set and forgotten. Operators adjust it on the move, using mechanical regulators at each wheel. The debate between electronic and mechanical control is more than technical. Early Trekol prototypes with electronic solenoids failed in winds at -50 degrees Celsius as actuator oil thickened and batteries lost charge. Mechanical regulators, relying on a spring-loaded valve and rotary knob, are immune to battery drain. The operator logs the pressure, turns the knob, and waits as the tire flexes outward. Adjustments happen in 5 kilopascal steps, with no risk of electronic freeze or sensor error. In the 2023 Katanga Ice Road Trial, a Trekol B60 covered over 12,000 kilometers without a single regulator failure. The only incident, a valve seal air leak, was fixed on the spot with a copper disc and a wrench. Mechanical systems answer the Arctic's demands. Electronics offer precision but falter in the cold, and simplicity endures when the thermometer plunges. This reliability is more than convenience, it is survival. When a convoy crosses thawing permafrost, the ability to bleed tire pressure down to 30 kilopascals can mean the difference between reaching the next depot and spending the night stranded, burning fuel to keep the engine block from freezing. Field logs from the Saka Yakutia Mineral Extraction Project show Avtoros Shaman units running between 35 and 60 kilopascals, logged over 25,000 hours with 0 regulator-related breakdowns. The large, deformable contact patch lets these vehicles cross snowdrifts, muskeg, even shallow water, where standard rigs would bog down in meters. Operators note the tactile reliability. Even in gloves, the regulator can be dialed by feel, and repairs need nothing more than a spanner and a patch kit. Ground pressure and tire footprint are the invisible foundation of Arctic mobility. The ultra-low pressure tire is not just a solution for soft ground, it is a calculated response to the physics of survival at -50 degrees Celsius. When the only way forward is over terrain that would trap ordinary trucks, the ability to float becomes the core of the expedition strategy. In the Arctic, tire pressure is not a detail, it is destiny. Wheel torque, not just engine power, sets the boundary between motion and immobilization on the Arctic frontier. In Siberian winter, the difference between horsepower and torque is not academic. Horsepower measures work done over time, top speed on a summer road. Torque is the force that turns the wheels, multiplied through every gear, transfer case, and axle reduction. In deep snow or thawing muskeg, it is torque that claws a vehicle forward when resistance triples and the ground itself tries to swallow the machine. A KamAZ Arctic truck, for example, starts with an engine output of 1,434 Newton meters at 1,100 revolutions per minute. But that is just the beginning. Through a first gear ratio of 4.1 to 1, a transfer case low range at 2.5 to 1, and a final drive axle at 4.2 to 1, the total multiplication exceeds 43 to 1. The result is over 61,000 Newton meters delivered to the wheels, more than 20 times the original engine torque. This is what lets a 15-ton truck crawl out of snowdrifts or drag a broken-down rig to safety, even when friction is reduced to a whisper. In these conditions, high revving horsepower is wasted. What matters is the slow, relentless push that keeps the convoy moving. A materials scientist at Moscow Polytechnic puts it plainly. Below -50 degrees Celsius, every metal remembers its crystalline structure. If your steel's brittle transition temperature is too high, it cracks like glass. Standard carbon steels, used in temperate climates, can become brittle at just minus 30 degrees Celsius. In the Arctic, that threshold is a death sentence for axles, gear teeth, and suspension arms. Russian engineers specify high-strength, low-alloy steels. 12% chromium molybdenum blends for KamAZ chassis, 30 kHGSA for the UAZ Hunter crossmember, each selected for a ductile to brittle transition temperature well below minus 60 degrees Celsius. This means the steel can flex under sudden loads without snapping, even after hundreds of freeze-thaw cycles. Elastomer seals and gaskets face their own crisis. Ordinary EPDM rubber, common in automotive O-rings, loses flexibility at minus 30 degrees Celsius and shatters at minus 45 degrees Celsius. In the Arctic, every seal is upgraded to fluorocarbon compounds, FKM or Viton, with a glass transition temperature below minus 60 degrees Celsius. In practical terms, a fluorocarbon O-ring remains pliable when the thermometer reads minus 55 degrees Celsius, preventing leaks in hydraulic lines and differentials. The margin matters. A failed seal can bleed out a gearbox or seize a steering ram, immobilizing a vehicle miles from help. Field mechanics in Yakutsk report that after 2014, the switch to domestic fluorocarbon seals eliminated the most common winter breakdown, cracked gaskets that once plagued KamAZ fleets. During cold snaps, gear reduction and material resilience work together. The transfer case, always manual in these platforms, offers a low-range selection with a ratio from 2.5 to 3 to 1. This multiplies torque but also slows wheel speed, reducing the risk of spinning tires and broken axles. The UAZ Hunter's transfer case, for instance, uses sliding dog clutches machined from cold-grade alloy steel, bolted to a ladder frame that can be re-arched or swapped in the field. The entire system is designed to be serviceable with hand tools, not diagnostic laptops. When the temperature drops, metal, if chosen wisely, endures. Fluorocarbon seals are just one example of cold-adapted polymers. Hydraulic hoses on the Tricol and of Toros Shaman platforms use PTFE liners reinforced with stainless steel braids to maintain flexibility and pressure integrity at minus 70 degrees Celsius. These choices are not over-engineering. They are the minimum required to keep critical systems functional when the environment punishes every shortcut. The physics toolkit for Arctic mobility is built on these three pillars: torque multiplication through deep gear reduction, materials with low ductile to brittle transition temperature and glass transition temperature margins, and a design philosophy that accepts no brittle failure. When a convoy faces a sudden whiteout or a hidden ice fissure, the ability to keep moving depends on each link in this chain. The next challenge is equally unforgiving. It is keeping fluids, oil, fuel, and hydraulic systems from freezing solid when even the best alloys can do nothing to help. Thermal management becomes the last line of defense. At minus 55, even the best insulated truck is only as reliable as its warmest circuit. On the Norilsk-Talnakh corridor, a convoy log from January 2019 records the moment theory met reality. 4 KamAZ 6345s stalled mid-route, their engines refusing to turn over. Diesel had gelled in the injectors despite Arctic-grade fuel. Battery voltage dropped so low that even the cabin lights flickered out. Crew statements are blunt. No start, no heat, no way back. The pre-start sequence, drilled into every operator, had been rushed. Cabin heater first, then fuel line heater, then battery blanket. Skipping the order meant the battery sat at minus 50. The fuel was thick as paste, and the hydraulic fluid was barely moving in the lines. A portable 5-kilowatt heater was hauled out and clamped to the fuel tank. It took 2 hours of forced air just to restore flow. Meanwhile, battery blankets rated for 200 watts wrapped the cells, raising them from ice cold to plus 20. Only then could the engines crank. Hydraulics, still sluggish, needed another cycle of inline warmers before steering returned. In these conditions, every minute lost to cold is a risk multiplied. The log concludes, checklist order is survival. Skip nothing. Thermal management is not a luxury, it is the fourth pillar. Without thermal management, torque, insulation, and ground pressure are meaningless. Racing upgrades and Dakar-derived tech mean little if the engine will not turn or the fuel will not flow. In the Arctic, heat is as critical as horsepower. Suspension geometry honed on Dakar stages now defines the backbone of the Arctic truck. KamAZ engineers took 45 centimeters of wheel travel from their rally program, enough articulation to keep tires pressed to the ground across deep snow and fractured ice, and built it into the civilian Arctic chassis. The double wishbone layout, paired with long-stroke gas-charged dampers, means every wheel can follow the terrain instead of riding above it. This isn't just for comfort. On the tundra, a tire that loses contact loses traction, and in a supply convoy that can strand a vehicle for days. The upgrades didn't stop at the suspension. After early Arctic deployments revealed axle failures under torsional loads, the axle housings were thickened with an extra 12 millimeters of steel. This single change increased torsional stiffness by 20%, cutting the risk of fatigue cracks that once sidelined trucks before they reached their destination. The same design, first tested on Dakar prototypes, now anchors the reliability of the 6345 and 6350 models. Cooling systems saw a similar leap. Borrowing from rally experience, KamAZ fitted larger radiators and thermostatically controlled fans, reducing engine overheat incidents that plagued earlier Arctic runs. The result? Trucks that can idle for hours at -50, crawl through snowdrifts, and then accelerate without thermal shutdown. A KamAZ master engineer summed it up. Every kilometer in the Arctic is won twice, first in the workshop, then on the ice. We learned from racing, but we build for survival. In the end, the racing upgrades are not for speed, but for certainty. What survives Dakar's dunes now conquers Siberia's frozen silence, proving that refined engineering, when shaped by the world's harshest lessons, delivers not just performance, but the power to endure. Right now, as Arctic commerce and climate science push deeper into uncharted cold, these machines remain irreplaceable. Their survival is not about legacy, it is about necessity. No algorithm or digital dashboard can make an engine start at -60 or haul freight when fuel thickens to wax. The world's most advanced frontiers still hinge on torque, redundancy, and repair by hand. That reality is not changing soon. Subscribe to follow this investigation into engineering where failure is not an option.